Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
In the Theano, in the pretty short term, we wanted to make it easier to do C extension related to Theano. This is something that is already documented, but the documentation is not the best, and we want to make that better, and we want also to make it easier. We have learned that some people just saw how to do it a little bit and was afraid of that, so we would try to make that simpler. We know that for for a big graph, 10,000 nodes and more, the compilation time itself can be slow, and we are working on that because the model, not just in the size of the weight, but in the number of nodes in the model, it just grow at the same time. So we are working on that. We continue to work on the multi-GPU to make it available inside Theano and not just inside the libGPU array. There is support for looping to make RNN and other such functionality, and our implementation works, but we will continue to make it better. There is some overhead issue in some case and other stuff like that. Right now, when we checkpoint some Theano function, depending how we do it, it can be done in such a way that it gets bind to the GPU. So when you want to reload it, you must have a GPU. So you train a full model and just want to see the weight later, you need a GPU just to visualize the weight, so that's not fun. And if there is a work around it, but they are not fun, so we will try to make it much simpler to be completely GPU transparent. I think it's the only place that is where we see the GPU that isn't transparent. Also right now in the Theano memory allocation, there's two modes. The default mode is during computation. When there's temporary memory that we don't need anymore, we will free them. And so at each Theano function call, we reallocate all the temporary memory region. There's another mode is where we keep all of them. And so the next call to the Theano function, you don't do any more allocation if the input size didn't change. But we can find something in between. For example, automatically find that some of the temporary elements are of the same shape and automatically share the storage and free it only when the last user of it. So we can have something in between that could be done automatically.
There's a trick for that in BW, which you might find handy, which is if you just have a counter of the number of times you use a piece of memory, then every 10 times you actually free it.
Yeah,
so the idea is that you do an amortized approach. So you're still going to be allocating memory occasionally,
yeah,
but the overhead of allocating memory will be reduced by a factor of 10, and then or whatever number you happen to choose.
I don't understand. When you finish using,
you don't need to figure out. You don't need to match shapes or figure out that things are taking the same amount. It's a very simple trick where you just keep a counter of the number of times that you would have freed it. You don't actually free it.
So you keep a buffer of available objects. That's one way to do it.
It's a different trick. So you have chunks of memory which have been allocated.
Yeah.
You have a counter associated with that chunk, and that counter goes up every time you call free on it. And then, but you don't actually free it unless the counter's value is equal to 10. And we set the counter to 0.
Maybe we can talk after.
Then GPU cannot swap out memory to it. If the memory is on the GPU, it will waste all the memory space. You have to be much
No.
more strict.
But on that side, on the GPU, in Theano, the way we plan to do it right now is when you build a Theano function, when it's compiled, all operations have already determined where they will be executed. So it will be static in the graph. It won't be something dynamic. So we can know where it is. That's something new. Yep. And there's a faster convolution that we are working on. Is pretty much done. We are trying to finish implementing the cafe convolution that use a call to BLAS and FFT convolution. We have already a working version, but there are more updates that can be done on them. libgpr, if there's other people interested to use it, the goal was to be common, but right now there is us. So we want more functionality as NumPy inside libgpr. Inside Python, inside Theano, I think we rapid mostly all of NumPy right now. We want to finish to move the functionality that we have in Theano inside libgpr and to the C level. And we want to be able to optimize the kernel selection depending of the GPU that we use.
So I'll mention a few. Okay. So I'll mention a few things that we're planning to do in PyLearn 2, but as mentioned before, a lot of these things are simply things that are currently being worked on in our lab that people have been implementing, and now it's just a matter of cleaning them up and pushing them to the public repository. So there are things like variational autoencoders or machine translation. Recurrent neural networks have been implemented in PyLearn 2, so it's another thing that's currently has a pull request open and just needs unit testing, and that'll go in. Documentation is still a big issue. You notice that as the user base grows, documentation becomes more and more important. So checkpoints are important, because training times can be very long, sometimes days, sometimes even weeks for some experiments. So we want to make sure it becomes almost transparent that when your process crashes or someone shuts down your computer, it automatically continues again, which right now requires a few lines of code. Better support for sparse data sets, better hyperparameter search supports. They're all this kind of examples of features that are up and coming to show that we're still extending.
What do you mean like better support of sparse?
Mostly that they're more efficiently stored in memory, and that right now there are certain parts where it actually needs to explicitly create the things in memory.
So it densifies sparse examples?
Sorry?
It densifies sparse examples?
Yeah, at some parts, which makes things very inefficient. And it doesn't really warn you or anything that it does that. But yeah, I think that's it. So if there are any questions, then.
So for the parameter selection, so what's the strategy behind that for selecting
Well,
parameters?
right now you can use whatever you want, but it's not automated. So if you want to do a hyperparameter search, you basically everyone does it. Some people just do it with a spreadsheet. Other people have written their own scripts or their own kind of things, but we don't have any system in PyLearn 2 that you can use to do a hyperparameter search, because everyone does it differently. Some people just kind of do it by touch. Other people just do a brute force search or grid search or whatever.
So you allow users to provide a layer way.
So yeah, so what we want to do is implement some sort of method so that people can do more intelligent ways of Bayesian optimization of the hyperparameters, but we need to create like a framework, like an infrastructure that allows people to implement that.
So I've been facing the same issue with VW, and I'm trying to figure out, so VW uses boost program options. I'm trying to figure out how to kind of automatically extract from the boost program options data structure sort of the set of options in a manner which could be fed into other algorithms.
Okay.
Have you thought about that?
Maybe I can talk a little bit more. The Hyper OPT is a separate project that exists. It was started by James Bertswa, one of the original author of Theano that moved after his studies. When one of his last paper, when he finished it in the lab, it was about random search on the hyperparameter is much better than the grid search. And then from there, he wanted to find something even better than random search, and that's what he was working on. So he finds some algorithm that find the better hyperparameter combination in less try than random search. And he also developed a framework where it is the user that this hyperparameter have this search space. And he also made sure that some hyperparameters are conditional on other hyperparameters. So it's the user that provides the search space of the hyperparameter. But it's not something trivial to make a good interface, just to describe that. So if you want, you can check more into HyperOPT. I'm sure on the mailing list they answer questions if you have question of how it's done. There's already a wrapping of that inside PyLearn 2 to make PyLearn 2 able to reuse it, but I'm not sure. Maybe it's in the pull request or it's merged, but in all cases it's not documented. So it's not much usable without significant effort.
Okay.